So, hello everyone. My name is Yasmine. Today I'm talking about remote sensing and data fusion and classification for urban feature extraction. I just had very recently, my Ph.D. degree in geomatics from Civil Engineering Department at Ryerson University, and I'm temporarily working as a seasonal lecturer and a postdoctoral research fellow at the same department. So I'll start with a brief introduction about the research topic that I've been doing, the objectives of the research, methods and the results, and we'll end up with some brief conclusions. So the world's urban residence ratio has been increasing, and it is expected to reach 70% by 2050. North America is not excluded from this urban sprawl, with 82% of its population living in urban areas. Okay. Yeah, so this is indeed the largest wave of urban growth in history, with social and economical consequences that leads or forces policymakers to detect, analyze, and evaluate current urban situations and develop new strategies to cope with the anticipated urbanization in the future. So the integration of 2D images and 3D LiDAR point clouds gathers the two components, the 3D geometric characteristics of LiDAR point clouds, and in addition to the dense radiometric information from the 2D images. Both together are believed to provide better discrimination between different ground objects and consequently better classification or urban mapping results. So, and just regarding this slide, the digital city is from the geometric or geomatics perspective. Digital city is a fundamental component of a smart city, and it relies on the integrating data that are acquired from different sensors, of course, in addition to GIS, Geographic Information System. So this integration, according to the scope of the research, relies mainly on two steps: the data registration and the data classification, or the classification of the LiDAR point clouds. So the previous researches or previous studies tended to use sharp identified features such as roofs or road intersections as control primitives, which are of course limited in this case to residential urban areas, and they are manually used to match or pair up these primitives manually. Regarding the classification, usually the produced urban maps are produced with a limited number of classes or limited land uses on the map, using high dimensional geometric oriented feature space with an overall mapping accuracy that barely passes 90%, or using multispectral LiDAR data in addition to calculating some indices such as normalized difference vegetation index with an overall mapping accuracy that didn't pass 95%. So the objectives of the research that I'm doing is number one, to integrate LiDAR and imagery data using for the first step by geo-registration, using data that are acquired in different flight missions, and by extracting control primitives that are not limited to conventional or traditional linear features, that are automatically matched, not manually, and that can accommodate different urban land uses. Second, the development of multi-level classification of LiDAR point clouds after being registered to the 2D datasets. And finally, to develop or construct a roadmap that compares different classification scenarios in terms of accuracies, classifiers, processing times, and best fitting mapping applications for each classification scenario. So the methods that I used in this research consist of mainly three steps: the LiDAR image data registration, the first multi-level classification of LiDAR point clouds, and a second multi-level classification of the same LiDAR point cloud dataset. So regarding the data registration, this is the flow chart that explains in details the steps that were taken to achieve the registration process. So mainly 3D LiDAR point clouds are converted to 2D LiDAR images. Then control primitives are selected, then they are matched together, then the registration model parameters are estimated. Finally, the registration model is validated. So in this slide, we can see 4 different urban morphologies visualized using 2D aerial photos represented by or visualized by RGB, or acquired in 3 bands, the red, green, and blue bands, and their corresponding LiDAR point clouds visualized by height in this slide. So I used the binding interpolation to convert 3D LiDAR point clouds into 2D images. And I ran a phase congruency filter to select candidate control points. So to isolate candidate control points, there are 2 approaches. The first is to fuse the phase congruency model with other edge detector algorithms, such as a high-pass filter, for example, or canny edge detector. The second alternative is the scene abstraction, and in this case, we cluster the scene into its basic elements, and we extract the outlines of those basic elements and the target points around target points within a buffer around those outlines as candidate control points. Then those candidate control points, the 2 sets of candidate control points on each data set, the 2D image and the LiDAR image, are matched automatically using the shape descriptor model. Finally, the registration parameters of the registration model were estimated using least squares in this study. Actually, this is mainly the Ph.D. study. So I used 4 empirical registration models. And here on those slides, we can see the LiDAR point clouds after inheriting the corresponding colors, the RGB colors from the corresponding aerial photo. So this is the first urban data set, the industrial urban. This is the second data set, the third and the fourth. So in all cases, the registration models are empirical, and they were estimated using least squares. This is a 5th LiDAR image dataset that covers a residential urban area, and it is the dataset that has been processed in the classification, in the subsequent classification analysis, as we will see. So the aerial image has 4 bands, or was acquired in 4 bands: red, green, blue, and near infrared. And the corresponding LiDAR data is the data are multispectral LiDAR data acquired in 3 different bands or channels, 1, 2, and 3, in addition, of course, to the height feature. So after the registration, here we can see the different visualization of the same LiDAR point cloud. So it is visualized using its original characteristics. The first channel, or the first band, the multispectral bands, originally exist in the LiDAR point cloud, and this is the height visualization, in addition to the RGB visualization and the near-infrared green and blue visualization to highlight the vegetation content in the scene. The last 2 visualizations are mainly depending on the radiometric characteristics inherited from the aerial images after the data registration. So to validate the registration process, the final control points were used. This set was used to calculate developmental accuracy, and an external set of checkpoints was used to calculate validation accuracy. And the metric here is the root mean square error. So the best registration model is the one whose both accuracies are close to each other with low root mean square error, in addition to, of course, qualitative validation, in order to avoid the problems of over-parameterization. So regarding the first multi-level classification, this flow chart illustrates the steps that were followed in order to achieve the first multi-level classification. So basically, it depends on ground filtering. First of all, this is the first step, training data collection, then constructing the classification scenarios, then doing the classification itself or running the classification models, then validating the classification models. So in the first step, ground filtering, which means separating ground points from non-ground points, and this was done using the 10 or the triangulated inverse network densification approach. This tool is embedded in LAS tools. And this multi-level classification is a point-based classification. So training samples were collected automatically using manually using Erdős Imagine, and 1% of the data was held for testing, and the remaining 99% was subdivided into 80% for data training, model training, and 20% for model validation. And those pie charts visualize the share of each observed class in the collected training data sets. So basically, 8 classes were observed in the scene, 4 ground classes, dark asphalt, light asphalt, sidewalks, and grass, in addition to 4 non-ground classes, buildings, vehicles, high vegetation, and low vegetation. So 4 classification scenarios were applied or were tested in this first multi-level classification. So the first scenario starts with the height and the single intensity, the only channel number 2, and the 3 remaining scenarios start to gradually accumulate the radiometric characteristics of the corresponding aerial photo. So RGB, then RGB near infrared, then RGB near infrared, in addition to NDVI. So in this classification, or in this multi-level classification, 4 classifiers were tried or tested: maximum likelihood, support vector machine, multi-layer perceptual neural networks, in addition to a voting technique to produce the final map. The classification was validated using sets or splits of train, test, and validation data sets, in addition to the k-fold cross validation. And the metric is the confusion matrix, with overall and per class accuracies represented by the user and producer accuracies. The second multi-level classification, mainly it's object-based classification, just to accommodate the misclassifications that were noticed in the first multi-level classification. So segmentation was a fundamental step to achieve this goal. So the data were segmented, training samples were collected, indices, geometric and radiometric indices were calculated, and then the classification scenarios were constructed. The classification was run itself, and then the classification model was validated. So it's pretty much the same, except for the segmentation step was fundamental before we start collecting the training data sets. So the segmentation was done using the color-based segmentation algorithm after introducing some enhancements to fit the scope or the objectives of this study. The training data sets were collected manually using on Erdős Imagine, and in this case, the format of the training data sets are segments. So 20% of the segments were held for testing the model, and the remaining 80% of the segments, the training segments, were subdivided into 80% for training and 20% for classification model validation. And those pie charts also show the share of each class in the collected training data sets in the segment format. So in this second multi-level classification, a vector of 25 calculated radiometric features was constructed fundamentally from the radiometric or the spectral properties of the point cloud, which divided between the multispectral characteristics of the LiDAR data itself, and in addition to the inherited radiometric characteristics from the aerial photo, RGB, and near infrared. On the other hand, another vector of 12 calculated geometric features was constructed fundamentally from the geometric properties of the LiDAR point cloud itself, mainly from X, Y, and the height of each point. So 10 scenarios were tested in this second multi-level classification, which is an object-based classification. So they start with the segment average of height, in addition to a single, dual, and triple intensities, alternatively up to scenario number 7. Scenario number 8 adds some radiometric characteristics from the aerial photo. Scenario number 9 uses all the calculated radiometric and geometric features, and scenario number 10 is uses the principal components of the features contributing to the classification scenario number 9. In this case, the classifier was only multi-layer perceptual neural networks. It was validated pretty much the same as what was done for the first multi-level classification, the point-based classification. So splits of trained test and validation datasets, k-fold cross-validation, and the metric is confusion metrics using overall and per class accuracies represented by the F1 score. So I'd like to show you some of the results that I got in this in my dissertation. So regarding the first multi-level classification, which is the point-based classification, we can notice that the scenario number 3 that includes the height, a single LiDAR intensity, and RGB near infrared from the aerial photo yielded the highest overall mapping accuracy that exceeded 97%, and the same scenario proved to be the most computationally efficient scenario, since the processing time did not exceed 25 minutes. And this processing time includes the training, validation, and testing the model. However, if we have a look here on the per class accuracy, all of them are above 90%, except for the vehicles and low vegetation. There is a significant misclassification of both classes together, because they share same spectral and geometric characteristics. Also, we can notice slightly another source of misclassification between buildings and high vegetation due to different acquisition times. Both datasets were acquired at different times, in addition to inexact ortho-rectification of the 2D aerial image. Finally, also a misclassification between dark asphalt and light asphalt due to shadow problems. Also, this is a major drawback of having a 2D aerial photo. So moving to the results of the second multi-level classification. So here we can see that overall, generally speaking, the overall mapping accuracy is increasing with the addition or with the inclusion of more features. This is highly seen during the last 3 scenarios, scenario number 8 up to scenario number 10. The per class accuracies followed more or less the same trend. So except for the 3 problematic classes, dark asphalt, light asphalt, and vehicles whose accuracies boomed during the last 3 scenarios, as well with the more inclusion of more calculated geometric and radiometric features. So we can see how their accuracies increased during the last 3 scenarios, from scenario 8 to up to scenario number 10. So scenario number 9 produced the highest non-ground overall non-ground accuracy, and scenario number 10 produced the highest ground accuracy. So the final map was produced using a combination of both scenarios with an overall mapping accuracy of that exceeded 98%. On the figure, the bar chart on the left-hand side, we can see the per class accuracies represented by the F1 score of all the classes resulting from the second multi-level classification. All of them are above 90%, and still we can see a relatively low per class accuracy for vehicles and dark asphalt, and also relatively in comparison to the rest of the classes. However, if we have a look on the bar chart on the right-hand side, that explains the difference between the per class accuracies of the LiDAR imagery before and after adding the calculated radiometric and geometric features. So all the per class accuracy increased after adding the calculated geometric and radiometric features. However, this increase is highlighted mainly in the vehicle class, whose accuracy developed or boomed from 88% to exceed 92%, highlighting the importance of adding or including the calculated radiometric and geometric features in the classification. So finally, this is the final urban thematic map that was produced, and with the misclassification still exists, but not as severe as resulted from the first multi-level classification. So they are marked and numbered in black. So in conclusion, the image filter, images were filtered using the PC model or phase congruency model at different spatial resolution, and it accommodated different urban morphologies. Candidate control points were selected using either filter fusion or scene abstraction approach after running the PC model. So final control points were selected or matched, paired up automatically using the shape descriptor model. The LiDAR image data geo-registration used the empirical registration models, and the registration accuracy ranged from 1 to 2 pixels. The first multi-level classification is a point-based classification, used or tested 3 different classifiers, 4 different scenarios, and the best scenario is the one that includes height, single LiDAR intensity, RGB, and near-infrared with an overall mapping accuracy that exceeded 97%. However, some misclassifications were reported. Afterwards, the data were segmented using the color-based segmentation algorithm after introducing some enhancements, and a second multi-level classification ran using it is mainly object-based classification using multi-layer perceptron classifier, testing 10 different classification scenarios, and the best classification scenarios are the one that includes the entirely calculated radiometric and geometric features in addition to their principal components, with an overall mapping accuracy that exceeds 98%. And this scenario has proved to eliminate the previously mentioned misclassifications. This work was published in IEEE Remote Sensing and SPIE, and it also was published in the ISPRS International Archives, and it was published as an abstract in the CSRS proceedings. It was also awarded the AOLS Graduate Student Geomatics Poster Award, the University Grad Showcase Academic Innovation Poster Award, the ISPRS Travel Grant, and Council Innovation Award twice. Since this is mainly the PhD work, I'd like to take the opportunity to thank my supervisor, Dr. Ahmed Shaker, and my co-supervisor, Dr. Yan. And this is the end of my presentation. Thanks a lot for coming and listening, and I hope you enjoy the Earth Day. So thank you.